Start the show. So there, officially welcome back. Happy Thursday. I've got the slides from last time pulled up to cue our memory, but I want to ask you folks, what did we talk about? Tell me what you remember from last time.
Different metrics for time.
Different metrics for time. And when is this a thing you need to be concerned about?
Accelerated designs.
Accelerated designs. Who wants to tell me what those are? Accelerated, yes. Otherwise known as cohort sequential or overlapping cohort. What's an accelerated design? Yes, when the time metric has both within and between variance. So when people differ in time when they start the study is the way that I would think about it. So if you sample people of different ages, if you sample children at different grades, if you're dealing with a patient population and people differ in how long they've had whatever condition you're studying, all of that. So that's what's known as an accelerated design. And in such cases, you might be tempted to just stick in, age or grade or length of time with the condition into the level 1 model because that's what makes the most sense. But the potential problem that you run into in doing so is what? In terms of model misspecification, what's the risk in just sticking in age or grade or length of time with the condition?
Convergence?
Convergence. Yeah, you're assuming convergence without testing it and doing so. What is convergence? What do you think? This is a new concept, one that we are going to go over many, many times throughout the semester. So this is your first taste of it, I would say. What is convergence? What is the idea of convergence with respect to between and within person variance in time? Okay, that's where we can start. Yeah.
I was like, I'm going to guess something gets more
please.
Similar.
You give me something to work with and I'll work with you, right? Give me some words and I'll make it work. Say, now give me a guess.
Something gets more similar as time goes on.
Something gets more similar as time goes on. Okay,
Separate the difference.
Things are becoming the same. So I'm gonna rephrase both of those answers into like the cohorts all map onto each other. They all converge onto the same trajectory. Like it doesn't matter when you join the trajectory, but you follow it just the same, even if you joined it later than somebody else. Like visually, the easiest way to explain it is this picture on the right here. All the little blocks representing separate cohorts align like that. So yes, convergence is another word for it. My word for it is smushing, meaning that you are forcing the effects of between person time to be the same effects as within person time. Otherwise known as conflation is another term for that. That's the more accepted term. And yes, we have to worry about this whenever the time metric of interest contains between person information. That's the big picture here. So we talked about, let's see, we had some data. We played with data. And these pictures were designed to illustrate the idea that on average, that one trajectory probably doesn't well describe anybody if there are age cohort effects. Cohort effects meaning that there are differences as a function of when you were a certain age, not just that you were that age. The real world example I gave was Mimi, my grandmother. I can't look at Mimi's trajectory and say that's what mine is going to look like necessarily. Beyond individual differences, there's a lot of reasons why somebody who was age 80 in, say, 2010 is going to be very different than someone who's age 80 in, doing the math in my head real quick, 2050-ish, something like that. I don't know. I can't do the math in my head. I can't do an equation in my head. I'm sorry. I can't. It's not within my working memory capacity, particularly while I'm on film, right, talking to people. so let's see here. So we discussed a little bit about the merits of time versus age as a level 1 predictor instead. So I think that might be a good place to pick up. So that was sort of the big picture gist of it. Does anyone want to ask any more specific questions or comments before we jump back in? No? No. So the argument that I'm trying to make here, let's fast forward a couple slides, is, by the way, this is another tip for building presentations. I never ever use animation in my presentation. Because if somebody has a different version of PowerPoint than you, there's no chance that, like, there's a very good chance it's not going to work correctly, and I found that out the hard way when giving an early career address, and all of my animation was like completely wrong and crazy, and I had to go through the talk that way. So whenever I want to do animation, I build separate slides, and I layer things in that way. Because then if you're running it as like a PowerPoint or a PDF or a web page or anything, it will look okay. So another pro tip from presentation land, don't do what I did. Animation is the death of you. All right, so it builds up to this slide here. And I had considered 3 potential, I would say, more explanatory time metrics in terms of, like, what is the causal process that's thought to be creating change in these cognitive outcomes? Is it the fact that as you get older, things go downhill? Is it the fact that as you get closer to death, things go downhill because there's failure of various cognitive and biological, neurological systems? Is it the fact that you have this disease that's causing plaques and tangles in your brain and all kinds of bad things that happen as a function of that? So all 3 of those are reasonable candidates for explaining, like, why change would happen over time. The way that they differ from each other is in the between person aspect, not the within person. Within persons, you are 1 year older every year, you're 1 year closer to death, and if you're a person who is on the dementia progression, you're 1 year, closer to diagnosis or from diagnosis. So within persons, time is just time. We can use that to our advantage because putting time into the model as our level 1 predictor means we are not assuming convergence. All we are using is the longitudinal information and saying, okay, here's where people started, and here's what happened after that. Now, why is that the case? We can then compare different potential causes, and I'm using this word in sort of a theoretical way. I know I can't establish causal inference anything because this is an observational data set. But is it age as a process that matters? Does age still matter after you control for disease progression? Does age still matter after you control for terminal decline? Those 3 things are alternative time invariant predictors. How old were you when the study started? How far were you from death when the study started? How much further were you into the dementia progression when the study started? Those can all become moderators. And to the extent that one of them explains more individual differences in intercepts and slopes than another, then that can lend some argument as to this is the thing we need to pay attention to, this is the important factor here. But as I mentioned last time, there are certain scholars who look at this time and study and go, this is ridiculous, this is not developmental. And so for those people, I did algebra. So I showed you this a little bit at the end of class, but I wanted to go back over it a little more carefully and then show you a worked example using Stata and R to estimate these models and give you some practice in actually trying to interpret these parameters, because that's the tricky part. So if I have this age-based model here, the key thing is that age has both between person information and within person. Do you remember how I could figure out how much is relative to each? Like what proportion is between? Can you think of a way to do that? Yeah. Pretend like age is an outcome, estimate an empty model, and calculate an ICC. If I remember correctly, age was 47% between. So of this variable that I'm thinking of conceptually as time varying level 1 within person, because it's part of my level 1 model, it's actually half between. It's half level 2. So that source of the information at level 2, some people are older than others when they start, can have its own set of effects in the model. So we have to allow the model to adapt to be able to introduce those separate potential effects of between person age. So this time metric, the accelerated time metric, age versus time, I've written out time in the way that I computed it in the data set to make a point. So we have, subscripts are important, remember, age ti, meaning time varying age, minus age at time 1, or it'll be time 0 in my example, but the first occasion is the point, and it only has an I. So what I'm trying to do here is literally subtract off the between person part. I'm trying to manually remove that source of variation so that all that I have left is how much time has passed since you walked in the door. That's what this variable is going to indicate. Either way, to keep the models equivalent, I have age at time 1 then as a level 2 predictor. So I'm centering it at 84. That way the intercept will have the same interpretation in both models. So when all is said and done, either way, the intercept is going to be the expected age at 84 for somebody who walked in the door at 84. It's the expected age at 84 in the age-based model because that's how age is centered, for somebody who walked in the door at 84 because of the level 2 predictor. In the time-based model, it's the expected age at time 0 for somebody who started at 84. That means they are 84 at time 0. So it works out to be exactly the same. So this main effect of age that's time invariant, this gamma O1, its job is essentially to unsmush the level 1 effect of age, gamma 10. So when both of these things are in the model, I've got the math here, writing this out, either way, the intercept is the expected outcome for an 84-year-old when they walk in the door. The within-person effect of time, or what is probably more accurately called the longitudinal effect, but I was trying to map onto, like I said, other people's presentations. The longitudinal effect is the same either way. Now, how does that happen is because in the time-based model in green here, I have removed the between-person part. So all that's left, if this variable for age now, or for time, excuse me, only carries within-person information, that's the only kind of effect it can have. So I fixed it like ahead of time. In the age-based model, it gets fixed behind the scenes due to partialing. After controlling for baseline age, the unique effect of time-varying age is the within effect. So what it brings to the table beyond baseline age is the within-person longitudinal effect, and that's why these two work out to be the exact same value, and they mean the same thing. Okay, with me so far? Maybe, yes? So a convergence model would say that gamma 10, so the level 1 effect of within-person time, and gamma O1, the level 2 between-person effect, are the same number. A convergence model would say that gamma 10 and O1 are the same thing. That the effect of being a year older when you walk in the door is the same as the effect of getting a year older after you're in the door. In many circumstances, that might be plausible. Like if you're studying over a very narrow age range, and you're studying a mostly homogeneous population where there's no reason why people would differ from year to year, that might be a reasonable thing. But if you're trying to stretch together like 30 years of adult data, that's not going to work. It's not going to work because the cross-sectional age gradient is going to be selected by non-random attrition. People who are old are not a random subset of the people who started when they were young. Okay, with me so far. Now the level 2 part. And yes, this is tricky. Yes, this is confusing. I have done my best to try and make it less so, but the only way it really gets less confusing is just repetition and exposure. So this is the first chance you're seeing this in this context. You're going to see it repeatedly throughout the semester. Because this is a concern for any predictor variable that is measured over time. It has a between part and a within part. And we have to be able to let the model separately estimate the effects of those two parts. So in these models, even though the variable that goes in at level 1, so the multiplier of beta 1 here is time in the green model on top here, and it's age in the bottom model, even though it's a separate variable, its slope ends up being the same. So the effective age and the effective time at level 1 end up being the same once you've included baseline age in the level 2 model. The level 2 model has exactly the same predictor in it either way, but its slope is different across models. Because what its job is different across two models. In the time-based model, and this is the easier way to think about it, the effective age at baseline is the same way you would think of any other moderator. For every year older you are when you walk in the door, you are this much lower or this much higher. It's just the effect of being older when you walk in the door, the effective age, period. And I would think of that as a cross-sectional effect or a between-person effect, a level 2 effect. In contrast, the effective baseline age in the age-based model is the unique effect after controlling for time-varying age. So it's not the same thing because it has this competition. It becomes what is known in the multi-level modeling literature more generally as a contextual level 2 effect. It is the effect of baseline age after controlling for current age. So a contextual effect is the effect of baseline age after controlling for current age. The between-person effect is the effect of baseline age not controlling for current age. Said more directly, the contextual effect is the test of whether it's okay to smush age. The contextual effect is your test of smushing. Does baseline age matter after controlling for current age? Then not everybody's aligned on the trajectory. If everybody's aligned, it shouldn't matter when they join the trajectory. Everybody follows the same trajectory. If baseline age matters, then not everybody's aligned, and you have these gaps in the trajectories, like in, let me find one of my pictures, like in this picture. This is a picture of age non-convergence, or when a smushed effect is not cool, and it matters when you join the study. Not everybody's on the same trajectory. Another way of thinking about the contextual effect, according to this picture here, this is slide 18, I'm going to zoom in a little bit. Let's look at age 86 as an anchor point, because I've got two lines there. The contextual effect is the vertical difference between the triangle and the square. They're both 86 at this point of prediction. The contextual effect is how much different you are as a function of when you started. It's this vertical distance right here. That's the contextual effect.
Is it the vertical distance from what the model says the trajectory should be?
Yes.
Okay.
Yeah, if they're,
those are technically two people, right?
they are representations of two cohorts. So this is the predicted trajectory according to the model for somebody who started at 80. This is a prediction for someone who started at 86. We can control for like how old are you supposed to be at a given occasion. If when they're both 86, this discrepancy is the contextual effect. And this is a positive contextual effect in this case, that people who joined later are doing better at the same age, which sounds weird until you think about who was able to join later. The highest performing people of the 86-year-olds. If there were no contextual effect, then you would see something like the purple line here, where there's really no vertical distance, and everything kind of aligns. So you don't need to know their baseline value, you just need to know where they're currently at, and that's enough to get yourself a decent prediction. So my perspective is, if you really want to keep your accelerated time metric, like you really want to use age or grade and you don't want to do time, then you can set the model up this way to get your contextual effect and see if that's okay. If it's non-significant and it stays that way no matter what you do, in theory, then you could be okay with respect to the fixed effects, because that's what we're talking about here. But if you do have contextual effects, then trying to interpret time-varying age in addition to baseline age is kind of a nightmare to talk about, and you're better off with age and time as two separate variables with two separate complete interpretations. Okay, how are we doing? I know, it's a lot. I'm going to reload. Okay, do I need to say any of that again? Because I'm happy to. Okay.
Can you explain the contextual effect for the time model again?
The contextual, so the time model does not have a contextual effect. The time model has the between effect instead. These slides are not designed to show that very well, but I can. Yeah, so the between effect would be the difference that goes both vertically and horizontally. It's not at the same point on the x-axis. We would have to have a plot where everybody is on the time axis. I have a picture that will answer that question better. It's at the very end of the handout. So this is the same data set, but not the same subsample, and I'm just looking at age versus time and not dementia and death. This is a subset of the sample that did not have dementia, so they should not be experiencing any like unpredicted decline, let's just say. So the bottom picture here is the x-axis is years in study. And the between effects that baseline age give you are, the main effect is represented here on the effect at the intercept. What is the difference as a function of baseline age in your time zero score? And then what is the difference in your slope as a function of baseline age? In the time model, that's what you get. So then you have like older people start out higher, older people decline faster, like those kinds of words. The age-based model, the contextual effect is the vertical distance at the same age after controlling for current age. And so this is where I had to make this picture in Excel because it would have, I don't know how to do this in any software package, including SAS, because what I had to do is show the parts of the predictions that are impossible given the way the data were designed, but what the model says. So like the model has an intercept at age 84. Well, if somebody started the study at age 88, I don't have a value for them at 84. But based on their trajectory, I can tell you what it should have been. And so the contextual effect is differences between age cohorts at the same age. The between effect is difference between age cohorts at the same time.
Repeat those two sentences.
Yes.
Again.
Okay.
I think I'm following you.
Yeah, we got
I
close,
steer
right?
it into
Yeah.
my brain.
Yep. Okay. And I just made this shit up too. Like, this is the first time I think I've said it that way. I should write this shit down for the next edition of my book. Okay. The effect of baseline age in the age-based model tells you differences as a function of cohort at the same age. The effects of baseline age in the time-based model tell you differences between cohorts at the same time, not the same age. And those sound like synonyms, but they're not.
I just want to make sure I'm following.
Okay.
It's the age on top,
Age on top,
time on bottom.
time on bottom. I could make either of these pictures from either model, though, Because as long as you have all of the predictors in the model and they all have the same potential effects, you can graph your data however you want. But it's the inference that you're trying to make here. It's like the age and age at baseline combination is evaluating differences from that, what's supposed to be a common trajectory based on age. Whereas we're not even trying to put people onto a common trajectory in the bottom. We're just saying, here you started, here's what happened. Now let's see what moderates that. The top picture is trying to align different people onto the same trajectory, but the results say it isn't working. Like, these are what you actually get, and it is not working. Whereas the bottom is not trying to do that. It's just representing the purely within-person information. Yes?
Yeah, I have two questions, Lisa. First, is this the reason why the random components are different later?
Yes.
Because the interpretation of what a 0 means in the intercept is different, right?
It ends up being the same once you fix it, but initially it is different, yes.
Okay. Do you
Yes.
have a picture for?
No. No, because this is something I learned like 10 minutes ago. So I don't have, no, that's only a slight exaggeration. That I don't quite have a whole developed thing to teach that yet, but it's the exact same problem on the random side. Because we're only talking about the fixed side right now. We haven't talked about the variance components yet.
Okay. So, and the second thing is, when we use a constant instead of a variable to center the level 1 predictor, the
Yes.
level 2 version of that level 1 predictor becomes a contextual effect.
Yes.
Why? Because there is variance at level 1 that have been not explained yet?
Yes. Yes, that is a way to think about it.
Okay.
So question from the Zoomers, still confused about the difference between and contextual. Yeah, join the club. This is hard. Like, this is one of the hardest things that I have to teach, and especially when everything is like the same variable. Let me go back to, this is hard. Am I raising my own hand? How the hell did that happen? Somehow I raised my own hand. Yeah, I do have a question. Why is this so damn hard? It's a rhetorical question, apparently. Let me go back to this one. Okay, so this is where we first introduced the language of between and contextual. So the difference between and contextual are both level 2 effects. Okay, they are both slopes that apply to baseline age as a time invariant cohort identifier. So rather than saying a baseline age, can I say cohort? Would that be easier? Maybe to make the nouns different? Or would that not make it better? Because like there's two kinds of age, and I feel like that gets hard to keep separate. So the way I think about baseline age is cohort. Like which generation is contributing to that common trajectory kind of thing. So if we call it cohort, so contextual and between are both slopes that multiply age at baseline as the cohort identifier. The difference between them is whether you've controlled for current age or not. If it's the cohort slope without controlling for current age, that's between. If it's the cohort slope after controlling for current age, that's contextual.
Because it's dependent upon characteristics at a particular time.
It's dependent on or conditioning on characteristics at a particular age. So, like time doesn't care. Like there's no way you can tell how old someone is just from this column. Whereas time varying age is both a function of how old you were when you started and what time it is. So it's two pieces of information put together. So after we control for what current age you are, what is the extra contribution of knowing what cohort you came from? That extra contribution idea of cohort, that's contextual. So after controlling for your current age, does it matter when you started? That's contextual. Yes, question, Carl.
We call it contextual because it's the idea of like my specific person effect in my
Yeah, my context, my generation. Like, let's hear it for Gen X, the forgotten generation, right? Everyone's all okay boomer and millennials eat avocado toast, but no one cares about Gen X. Yeah, it's my context. No, seriously, it's a thing. Proud member of Gen X. Yes, contextual. That's a good way to think about it. So it's like, what does it matter beyond, like, what cohort you came from, what generation you came from, what year you started? Yes.
Yeah. Can you go back to slide 36, please?
I can try.
36, that one, yes.
Okay.
I think that, well, in this case, it is easier to understand this if you read the chapter 8, because...
Yes.
Yes. So that's helpful. In this case, Lisa, the cross-interaction or zero cross-interaction effect that gamma O1 in both models...
Yes.
No, the O1.
O1, this
Yes,
one.
Yes, exactly. So they are trying to explain why people were different in the time in the study, at the beginning of the study and in the age base, at the beginning of age 6 or at the beginning of age equal 84.
84.
Okay, gotcha.
Yep. Yes. So there is a reason why this is chapter 10, and I did skip 8 and 9 temporarily. And so in planning this class and in planning the book, I had to decide like what order to put things in. And I decided to go in a different order because I thought, like, we're not going to deal with other time-varying predictors. We're just going to do the age part first. But then all of the concepts of those earlier chapters with respect to time-varying predictors are necessary. I'm just, like I said, I'm just introducing you to the ideas at this point. The big picture, as tall as I can make it, is that any level 1 predictor has level 2 variance too. Almost every case. In the same way that any outcome has level 2 variance. Like, for the reasons that we had to do a multi-level model in the first place, we have to care about this on the predictor side. The univariate approach to these models requires us to either manually carve up our variables into the 2 levels or put in enough controls to where the model does it for us. The latter of putting in all the controls requires a different interpretation because you're controlling for cohort, not introducing cohort. Maybe that's a better way to say it. Let me say that again. In the time-based model, you are introducing the effective cohort for the first time. In the age-based model, you are controlling for it. Maybe that's better. I'm going to keep making shit up until something sticks. That's what I'm going to do. Did I see a hand?
Yes.
Okay.
Lisa, at the end of the slides, well, or at the end of part 2 in chapter 10, you explained that we can use time as time, or the time in a study model, to try to see if the other metrics of time at level 2 contribute or not to predict the random intercept.
Yes.
Is that similar to the idea of double decomposition we read?
Yes, yes. So the question was, like, if you use a time-based model, which is where I'm going to end on this because it's easier. It's just easier and you can't be wrong because you're not trying to align people at all. You're just letting them do what they want and then seeing what moderates your trajectories. So that's where I'm going to land on this. So the idea of then making it an empirical question, does age matter? Or is it years to death that matters? Or is it years to dementia that matters? Or whatever other thing. Those are alternative ways of sort of aligning people that you can phrase as testable hypothesis. And the reading that I gave you, the double decomposition, has 2 different level 2s in the same vein as that. So the reading is about the Flynn effect, the idea that intelligence scores are like increasing over time, and why is that? And so I like that paper quite a bit. To be fair, I was reviewer 1 on that paper, so I was invested in its success. And they have a very interesting data set in which they can pull apart these multiple sources of time as well. And I did want to try and incorporate some of that into chapter 10 in the book's revision. So, yeah, I signed a contract to revise the book in 2018, and it's only 5 years late. So I'm off to a great start. Okay, where was I? Is this helping at all? We're getting there a little bit. Yeah, big picture. Time, if it has level 2 and level 1, Those are two different things. That's the big picture. Don't put them together because you're probably going to be wrong. Yes.
So, I don't know if I'm just like catching up or something here, but I'm trying to write down if there is a non-zero contextual effect when you smush between within person variance into your time metric, then you have a problem.
Yes. Yes, I would agree with that sentence. If your contextual effect is non-zero, that means that you can't align people the way you're trying to. And good luck trying to describe to someone the differences between age and baseline age at that point. Like, it's just, it hurts. The mental gymnastics you have to do hurts. And so, especially at that point, I would switch to time. And if reviewer 3 gives you crap, be like, algebra! I can make the models equivalent. Using time does not mean that you're making, like, you know, that it's not a developmental study anymore or that you're atheoretical. It just means that you are taking the longitudinal part of time and isolating it so that you can get a cleaner picture as to what the between factors would be. So this result, by the way, this is specific to when I have only a random intercept. So note there's only one U on this page. And it's specific to when I have a linear effect at level 1 and I have a linear effect of the level 2 component at level 2. This combination of either way, you can get contextual as between minus within. You can get to between as contextual plus within. This is a very well-known result, this combination right here. The unique contribution, dare I say, what I tried to do with this is to show that even if you make the model more complicated and nonlinear in the variables, you can still get back to an equivalency. So in this model, what I have added is a cross-level interaction. So where that would be in the previous slide is adding baseline age right here as a moderator of the slope. So I'm saying that your initial value can depend on your baseline age cohort, and so can your slope. That's a reasonable thing, one would think. But to be able to unsmush that interaction, to make sure that it's only the within slope that is being moderated by cohort, you need a quadratic main effect of cohort. If you work out the math, and it's in chapter 10, and it's also probably in the other chapter I gave you to some degree, the only way that you can make the time and age-based models equivalent is with this additional quadratic term. Once you do that, you get the same intercept either way. You get the same linear effect of level 1 time or age. You get either a between effect or a cohort effect for the contextual effect, and you can figure out one from the other with respect to the level 2 effects. So because we have this cross-level interaction, we need baseline age squared to allow the between and within parts of time to be moderated by baseline age separately. And if you add, there's one more I did then, if you add a quadratic slope at level 1, then it's still equivalent so long as you have a quadratic slope at level 2, but then the equivalency is just a little bit more complicated. Do I need you to fully appreciate this or be able to replicate the algebra? No, not at all. My point was to demonstrate that you can get literally the same likelihood, the same model predictions, and the fixed effects or linear combinations of each other if you use age at level 1, so long as you have controlled for cohort on every corresponding term. Where corresponding means the quadratic effect of baseline age is needed for the cross-level interaction and or the quadratic level 1 term. Now, where this falls apart, random effects. And I only need to show you the simplest model to make this point. It gets even worse if you use non-simpler models. So this is slide 40. So here's my time-based model written out in composite form. where if I add in a random slope, that's right here, this U1 thing, it's multiplying age minus age at baseline as time, or in the age-based model, it's multiplying age and age at baseline. Whereas down in, or excuse me, this part is, it's being subtracted off once you carry through the minus. Down here, age is not being distinguished. So now they're not the same. If you add a random slope, in the time model, the random slope is being applied only to the within part because you're subtracting off the between. In the age-based model, it's being applied to both. Now we're back to smushing again, but it's smushing of a variance component and not a fixed effect. And this is something that has bothered me for years, to be honest. Like, I knew they're not the same, and so then I went down the rabbit hole of like, well, how do you figure this out then? Well, the reasoning that I had as to why the models on the random side might not be the same is because of what the intercept means. So if I just look at the random parts, a random intercept is conditional on the zero value of any slope that's random. So like if I have a random intercept only model and then I throw in a random time slope, the random intercept becomes specific to time zero. It would be different at any other point because a random time slope means people spread out, right? So the vertical distances have to change. So in the top model, the random intercept is at time zero, and at the bottom model, the random intercept is at age 84. Those are not the same thing. And if you think about how reliably somebody's intercept could be estimated, everybody has a time zero. Unless you join the study late or something, but even then time zero is pretty close to where your data would be. Not everybody has an age 84. Like if I started at 90, I don't have an age 84. So Radenbush and Breik in their textbook had talked about this as involving like greater extrapolation to where the intercept is, which would cause maybe less reliability and more shrinkage. If there's greater shrinkage of the intercepts, that can propagate to the slopes. And so in their textbook, when they talked about this problem, they suggested doing what is the equivalent of the time-based model, which is known as group mean centering or cluster mean centering more generally. And they said, and they showed one data set in which the random slope variance was greater under the time-based type model than the age-based type model. And I was like, okay, cool. I now understand why this is. I did not come up with this part. There is a new reading on your reading list for like about 3 weeks from now that I added. It's in Icon, so you can download that, and we'll talk more about that later, but I understand now what happened. This happened in my data, by the way. So when I put in age as my level 1 variable and gave it a random slope versus the equivalent model with respect to the fixed effects, and I gave time a level 1 slope, the variance was much bigger in every case. Model fit was the same. So then I had done a simulation. Again, I told you this has been bothering me for a very long time. So this is a poster I presented in like 2008. And I did a simulation. And I did 4 combinations where I simulated with an age-based model, fit the age model, simulated with time, fit age, simulated, all the 4. I can't do it in front of you guys. And I found basically that the greater the amount of between-person age information, the more bias there was in the slope. So it looked like they were right, but I couldn't figure out why. And the answer is smushing. Very briefly, again, talking more about this later, but just to tell you very briefly what happens. Do you remember what happens to the predicted variance, covariance over time when you add a random slope? So if I only have a random intercept, what is my pattern of variance over time like? Compound symmetry. What does compound symmetry mean? Constant. Yeah, so it's U plus E on the diagonal, and U0 variance is the covariances, right? Constant variance and covariance. What is the pattern that it becomes if you add a random time slope? What kind of variance does it predict? Heterogeneous, but in a particular pattern. Quadratic. So the variance, the new formula for the variance has time squared as a piece of it, and that's why it goes like this. It's parabola. So this model basically says that the age-based model says that that parabola of changing variance applies equally to baseline age as it does time, because they're both buried in this variable still. So it's a like heterogeneity smushing, if you will. Whereas it's literally being subtracted out here, and so the random slope only applies to the within part in the time-based model. So it's another kind of convergence or smushing on the random side with respect to heterogeneity of variance. And it turns out that once you put in the right terms to make everything equal, you do get spot on the same things. But it is nearly impossible to get that model to estimate, is what I have seen so far. And I have a whole handout to tell you about that. So I'll show you what I mean by that. But this is a smushing of a heterogeneity pattern, is the take-home message. That's why this is a problem. All right. Yeah. Okay, so the winner is time. That's the take-home message of the talk here. Tracking change as a function of time and study represents it directly, parsimoniously, makes no assumptions about how people align onto a trajectory, doesn't assume any contextual effects are zero, doesn't assume age convergence. It permits people who don't necessarily have certain events. So like if you're going to do a time metric of like years till death, everybody has to be dead for you to like know where they are. Whereas you could put something in like not dead yet, as dead or not dead, and then how many years to death, something like that as a predictor. You could include people who haven't experienced a critical event that you would otherwise use to create a time metric. So then at the end of chapter 10, I demonstrated that you can put in both baseline age and baseline years to death as moderators and show whether one contributes incrementally above the other. So then you can test, you can basically phrase it as competing hypotheses as to what is the mechanism of change. Like how should I align people? And that's that. And then one last thing, if you've heard of retest models, this is a thing in cognitive aging. Yeah, those assume no cohort effects too. So you can either control for cohort or you can control for retest, but not both, because we don't know what the cause of non-convergence is. So that's a whole separate presentation, but I had to steal a slide about that just because this is a thing. All right, the end. I have destroyed your will to live, I can tell. I don't take it personally. Yes?
Can you go back to slide 40, please? A minute?
Yep.
Because I have a question related to that unconflated random effect in time as age. Yeah, that green box there.
Mm-hmm.
So in that case, Lisa, that unconflated random effect will represent the variance around the average growth curve around time.
Yep.
Okay, that's all what I need.
Yep. Yeah, no, it means the same thing, right? It's you know, each person gets their own slope deviation from the average slope. It's just a question of whether you're including age as part of like where they should be. Yeah.
Now, good question, because you said that we usually cannot compute random effects for level 2 variables, right? But
I know.
in this case, if we don't do that, we would be combining the effects of the level 1 and level 2
Yes.
variances. But if we cannot compute that level 2 variance, could we subtract that smushed effect with this new unconflated term to have some kind of level 2 random effect? Is that weird?
Yes, that is how you make these equivalent, is that you have to put in a random slope for the level 2 predictor, which is like the first thing I told you can't do. It's not really a slope, it's a heterogeneity term. But if you can't do that, then it is allowed, and probably your only course of action, to have time as the predictor that gets the random slope, and you could still have age as the predictor that gets the fixed slope with all the cohort effects and contextual effects. A different variable could have the fixed effect than has the random effect. That is allowed. It's tricky and confusing, but it is allowed. And that's what I would do if you really want the age-based model, is I would fit a time random slope instead. Yep. Okay, other questions? Do you want to see an example? Yeah, I thought as much. And this will spill over into next week, but I'm fine with that. I sort of expected that it would. This example is brand spanking new. I had an example that was on this topic from 5-6 years ago, and I ditched it and started over. Partly because it only used SAS, but partly because my thinking on the topic has changed. So this is example 2, part 1, because part 2 is going to be using the exact same data and set of models to show you how to fit this using SEM software. That's what part 2 is going to be. So trying to build on the facilitation comparing the two here. Yes, glad the Zoomers are excited for an example. So this is data from chapter 10, which means it's on the Piles of Variance website, and you can play with it on your own, however you wish. And in this example, I have Stata and R, because I think no one else who uses SAS doesn't also use one of those two programs. But I think I put, yes, I know I did. I put the SAS code for this example inside the same download folder, because I still tend to run things there just to make sure that I have converging pieces of information. So I'm going to add that. There. Now I have SAS in the folder. I'll update this later. So this is the same story. These are old people, old twin pairs. I selected only one person out of each pair, so I don't have any twin dependency. Otherwise, I would need a 3-level model, and that's coming at the end of the course. Because this is enough, right? Can we agree that this is enough? Yes, that's what I thought. So these are people from that same sample who never had dementia. So they are sort of normal aging people. I have 207 of them and 557 observations altogether. So there's a lot of missing data, as you might imagine. I'm centering age at 85 years in this example, is it? No, 84. Yeah, I stayed with 84. There we go. Fix that too. And the data manipulation steps require us to start with the time varying variables, but then also create the time variables out of what we have. So this is a long data set, like usual. 1 row per occasion per person, and the variables that I already have are time varying age, and I have age at time 0 as a variable, and that's analogous to the data structure that was in here. So this is basically what it looks like, where I have age at time 1 is what I called it here, but it's time 0 technically with respect to how I centered time. So I made a couple of rounded variables so that I could make some pictures, just to get a sense of like what the trajectories look like. So I have, let's see here, we'll start with the Stata code here. I'm making time as time varying age minus age at time 0. I'm making a squared version because the formulas get really ugly otherwise. So I'm trying to make it a little bit easier to understand and read. Somebody rounded up actually up to occasion 9, so I put them back to 8 to make a picture. I did the same thing. I generated a variable called rounded age out of time varying age rounded to the nearest year. I'm not modeling with these, I'm just making pictures, okay? And rounded some people into convenient intervals here. Squared versions of time varying age minus 84 and age at baseline minus 84. So 84 is like the centering point of everything. And I'm making sure that everybody in the data set has all of the variables that we're going to be using, because otherwise those cases are going to get dropped. So when we move into an SEM framework, that will not be necessary. You can have missingness on predictors if you're willing to bring them into the likelihood. Let's see, not SAS code, this is R code. Yeah, I don't think there's anything new here relative to what you're used to seeing. So I have the same process here. I read in, yeah, let's see, SAS data. And here's the descriptive statistics for these things. So I have Stata first. So the mean age at time 0 was 82. So I'm centering it at 84. The range is 79 to 97. The range of time varying age is up to 99. Time goes until about 8.5. So this is roughly balanced time, but not quite. Recall is on a scale of 0 to 16. And then one thing I wanted to point out, time varying age and age at baseline are correlated quite strongly, as you might imagine. But age at time 0 and time are also negatively correlated. So that means that there are fewer of the longer occasions in people who are older, as you might imagine. So because of this correlation right here, I can't say I have between age versus within age as two uncorrelated pieces. The way that I would have had to do it to get to that is to use mean age over time rather than age at time 0. If I use mean age over time as my centering, then age and time would have been completely unrelated. The reason that I didn't do it that way is because of missing data. So if I have two people who start the study at 85, and one person goes all the way through the 8 years, and one person only does 2 years, the person who made it all the way has a higher mean age, even though they're from the same cohort. So I wanted age to represent cohort more than like length of being in the study, so I chose to keep it as age at time 0. So what I can say is that age at time 0 represents cross-sectional differences in age that were there to begin with, and time represents longitudinal differences in age as a function of progression in the study. I can say that. And same stuff in R as well. Okay. So how do I know if I'm dealing with an accelerated time metric? Let's say that you're a data analyst on a project. You get handed a data set. Could happen. The people that you're working with don't have a very well documented data set. Also could happen. How do I find out if I need to worry about this? How do I find out if my metric of time potentially has between person variation in it to be worrying about? Yeah, well, that is model comparison of this kind of model, right? So I am fitting mixed with time varying age as an outcome here, and doing the Elmer call, predicting time varying age as an outcome. We haven't done this yet, but there's no reason that you can't. It's a continuous variable. Question?
I don't know if my brain is shut off. Time varying age.
Mm-hmm.
Can you explain that one more time? What that refers to?
Time varying age is a column that looks like this. So it's literally like how old you are at each occasion.
Okay.
And so that is a function of how old you are when you started and which occasion it is, both at the same time. So the purpose of this initial analysis is to figure out how much of this variation is actually due to where you started. And this strategy more generally, any longitudinal data set, if you're not sure if a given variable is level 1 or level 2, this is how you answer that question. Empty means random intercept model, treating it as an outcome. A couple new things here. So in the Stata documentation, it now defaults to printing variances instead of standard deviations. It's done that for, I think, a few versions now, and so I dropped the word variance out of the code. I've also switched to MLE and REML equals false. Can you guess what those stand for? Yeah, maximum likelihood as opposed to what? REML, which stands for residual or restricted. You can take your pick as to what the R means. Why might I have done that? Yeah, I'm interested in comparing models that have different fixed effects, and I need to be in maximum likelihood in order to do that with -2 log likelihood AIC or BIC. That reminds me, actually, speaking of reviewing some basic stuff like that you probably already know, and if you don't, then this is a great time to remind yourself. That reminds me, let's see, yes, your homework 1 effort draft is due on Monday night, in which this is one of the questions, cough, cough. So if you're using residual maximum likelihood, the only kind of model comparisons you can do are with respect to the model for the variance, holding the fixed effects constant. If you're in regular flavor maximum likelihood, you can do any kind of comparison you want. Regular flavor maximum likelihood is the only choice of maximum likelihood in SEM packages, which is another reason so that I can compare the output from M+ and get the same thing. Regular flavor maximum likelihood is what everything else is. Multi-level models is really the only case in which you'll see REML. So when I partition the variability in age, I get variance of the constant, or the intercept as it's otherwise known, is 5, and variance of the residual is 7. Intraclass correlation then is about 0.4. Here is the same information out of R's Elmer call. So 40% of the variability has to do with which cohort you're from. The other 60% is your current age during the study. So I know right off the bat that the 40% of this variable that has level 2 variance, that has an effect. The other 60% has a different effect. It's an empirical question whether we can squish those to be the same thing. Now, for purposes of demonstration only, because I already know what's going to happen, I put time in as an outcome. So Elmer call here as well, predicting time. And I get back 0 to the 20th decimal place for the intercept variance, and an interclass correlation of 0 to 21 decimal places or so. Surprising or not? Not surprising, right? Time is supposed to be only within person, so this is just reminding you, like, that's what that means. So if we put time into the model, the only possible interpretation of its effect is a within-person effect, because that's the only kind of information it has, on purpose, deliberately. How about recall, our outcome variable? So now I'm throwing in some formulas so that we can add to them as we move on here. So our 2-level notation. No log, by the way, state of people means don't print all the iteration history stuff. So I found that to shut it off. So it shortens things a little bit. Recall, on average, is about 9.7 on a scale of 0 to 16. I think it's a number correct variable, and yes, it should have been a different distribution, but this was hard enough. Yes, this should have been a 3-level generalized multi-level model, but this is hard enough. Sometimes you have to take some shortcuts just to make it, like, go in the first place and then not make everyone's heads blow up at the same time. 10 over 10 plus 5, intraclass correlation for recall is about 67% of the variance. So that means 67% is what? Between or within? Between. Yes, indeed. Level 2, due to mean differences. Some people are better at recall than others. Oh, all the time. Probably true.
That's at time 0, right?
This is at no time or no age because it's not in the model yet. So this is empty.
Oh.
Empty. No, nothing in here but random intercept, residual, and a fixed intercept. Yep. So I know that this model isn't right. Like, this statement that it's 67% between is just like a descriptive starting point, because once we put in random slopes, what that means is that the variance has to change over time. So an interclass correlation is like an average of what it would be all the way across time once we fit the model. So this is a simplification, but it's a useful thing to report. People like to see it. So here is then the R output for the same thing. This, I am changing the way that I spit out the output so that it matches the other programs. So I am calling LLIKAIC so that it can print deviance to enough decimal places for your homework, because the global option to print more decimal places does not work for this. And I tried taking the quotes off, as you had said, Nathan, and it still doesn't work. So yeah, I was like, screw it, I'm just going to ask for it. So you get AIC, BIC, log likelihood, and then minus 2 times log likelihood is this number called deviance right here. So there's my random intercept variance for recall. Here's my residual variance for recall. My fixed intercept that tells me the average, so the mean of the person means, and then my interclass correlation. Then last thing I'll show you, since we're about out of time for today, pictures. Another thing, if someone hands you a data set and you're like, well, what kind of model do you want? I don't know, that's your job, figure it out. True, right? Some of you are like, yeah, I know what that's like. Once you figure out if there's any dead people in the data set that have data that don't need to, or recall scores of 16,000 instead of 16, you know, once you figured out all that stuff, I will tell you that I have been handed many, 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 many data sets in my lifetime, and a lot of times people have been said, oh, it's already been checked and cleaned, it should be ready to go. Guess how many times it was indeed checked and perfectly ready to go? Never. It has never happened yet, ever. Do not trust the PIs when they tell you this. Do your own checks.
Half the time I open up files that I cleaned and I'm like, what the hell, Nikki?
Yes, like, is it possible to have a recall score of 16,000? Just asking. And that's an easy mistake, because that'd be 16,000 with the comma instead of a period or whatever. Anyway, rounded age. So I am fitting a saturated means random intercept model. So I have I dot rounded age here in Stata and I dot occasion to make these plots right here, just to get a sense of like what the overall trajectory would look like. The confidence interval around the trajectory is also helpful. So there's not very many people who contributed data at age 79, so we have a really wide window there. It looks sort of flat-ish and then maybe down and then back up again. So this down and back up again is probably an artifact of different cohorts. The people who are still alive to be contributing data at 90 and 95 are not part of the same trajectory. Occasion and study is like fine, 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 not fine for some reason, although the difference in score is about 2 here. So there's not a whole lot of useful information here in terms of like pointing me towards a very specific kind of model. I'll throw some polynomials at it. R code, I was able to do this by doing as factor in this, and then I had to have Jonathan help me make the pictures. So there's R code online that he sat down and wrote. I'm giving him full credit. He literally said, move out of the way on my keyboard. Well, first he yelled because it was a Windows keyboard and none of the places worked the same as the Mac. But then once we got over that hump, then he yelled because I have a sideways mouse that goes like this, because it hurts my hand otherwise. And so once we got over those, like, you know, curves, then he was able to make code to make the picture. So basically what we had to do is take the output from this model that is a list where it had like a table that's not a data set and convert it into something that is like a data set, extract the information from the rows as to which age is which and save it as a column, and then make the picture. So there's code online that does that. All right. So I don't have any strong hypotheses other than maybe it's a little bit bendy. I'm going to throw quadratic models at it, and that we will do next time. All right. Any other questions before we call it a week? Not just a day, but a week.
How do you know when you can smush it or not?
The answer is never. You can never smush it.
It's never okay to smush.
In my opinion, no, it is not.
Okay.
But I can show you which parameters directly speak to that. They are going to be the level 2 effects when you have a level 1 variable that still has the between part in it. That those will be the parameters that speak to that. All right. Then I shall hang it up. Oh, one more question? Yeah, go for it. It's 1:44. We're not out of time yet.
So moving forward here, we're going to be taking our time-varying variables, whatever they might be, the ones that we're suspicious have smushed within person variance. We're going to put them, we're going to put them in as an outcome in our empty means random intercept model.
Yes?
Compute the ICC, and then do a likelihood ratio test to see if the random intercept improves
Yes, so more generally, any level 1 predictor that we're suspicious of having level 2 variance, it could be time or it could be something else, you can see if it has level 2 variance, and if it does, then you have to do something about that. Person mean center or represent the equivalent variable at level 2, which would be like cohort in this case. Yep. And yeah, you can get a significance test as a model comparison as to whether that ICC is different than 0. Yep.
What would be a clustered example?
Kids in schools, like socioeconomic status is like kids are not randomly assigned to schools. Like rich kids all go to the same school. So is SES a cohort thing or a kid thing? It's both. If you're a poor kid, is it better to go to a school where there's lots of rich kids? Probably. So after you control for whether you're poor, does it matter how poor your school is? That's a contextual effect. It makes a lot more sense in that context, but that's not till the fall.
Yeah.
All right. Thank you for being here. Have a good weekend. Let me know if you need anything. Homework 1 is due on Monday night, please. I have office hours on Monday if you want to talk to me about it. Until then, bye, Zoomers. I do need to save. There we go.